welcome to the deep...
That sounds like actual torture.
Right, like capital T, the space, capital Q, quick, space, comma.
You would completely lose your mind. You wouldn't comprehend a single word of the story.
Exactly. You throw the book across the room.
And that megaphone effect is the reality of a poorly configured terminal environment.
Yeah, it really is.
When you are trying to comprehend the flow of a program, like the actual story the code is executing,
Right.
having the grammatical mechanics of that execution blasted at you, it just pushes the actual evidence you need completely off the screen.
You're just left scrolling endlessly.
Exactly. Scrolling for days just to find a single error state. It raises a really critical point about how we balance signal and noise when we're building internal tools.
Because whenever a system generates information, the architecture itself has to dictate what is useful context and what is strictly noise.
Right. It's not just a Haskell problem, it's a universal data problem.
So let's set the specific scene from Ang's notes to see this in practice. Ang is working on a Haskell program designed to parse a Chinese text file.
Okay, so reading through a raw document.
Yeah, reading through the raw document and breaking it down into structured tokens.
Like categorizing the pieces of the text.
Exactly. It is identifying the metadata, like the title and author.
Right.
And it is identifying the headers, mapping out what is a volume and what is a chapter.
Gotcha.
And finally, it is identifying the actual paragraphs, like the bulk text of the document itself.
And I should point out, the underlying goal of this parsing is quite robust, too. The notes indicate this tool uses a specific type, an export format type.
Oh, right, for the output.
Yeah. It's designed to eventually handle outputting to TIP, EPUB, TXT, and Markdown files.
Wow. So that's a lot of different formats to support.
It is. So we are looking at a system built to ingest raw, unstructured text and perfectly map it to entirely different publishing formats.
It means the logic has to be perfect.
Exactly. To do that reliably, the parsing logic has to be airtight. There's no room for sloppy categorizing.
Which brings us to the friction point Ang ran into. While the program is executing this parsing logic, it generates a debug log for the developer.
Naturally, you need to see what it's doing.
Right, but it logs the processing of all these different types of tokens simultaneously.
Oh, I see where this is going.
Yeah, metadata, headers, paragraphs, it all just floods the standard output at once.
The megaphone.
The megaphone is fully on. The program is technically working, but it is communicating far too much.
Right. The developer cannot verify if the parsing logic is sound because the sheer volume of output creates this massive bottleneck.
It's right in their ear. So what does Ang do?
Well, rather than attempting to write some, complex, detached logging class from scratch to handle this...
A lot of people would do.
Oh, absolutely. They'd over-engineer it. But Ang looks backward to move forward. They look to a previous project for the architectural blueprint.
Oh, the TXT2 book project.
Exactly. The source material mentions this past project called TXT2 book, and the experience gained building that specific tool provided the exact concept needed for this log flooding problem.
The verbosity counting flag.
The verbosity counting flag. It is a concept that directly addresses the human-computer interaction layer before even touching the back-end logic.
So let's break down what that actually looks like for you, the user. The user feels this interface primarily through a tactile, adjustable dial on the command line.
Right, it's a dial.
When the developer runs the parser, they append a flag to control that megaphone. If they type a single -V, they set the dial to the first level.
And what does level 1 give them?
In this program, -V translates to only show the metadata tokens. Keep it quiet, just give me the title and author.
That makes sense. Establish the baseline.
Exactly. But if they type -VV, the dial turns up.
Level 2.
Level 2. The program now outputs metadata and the header tokens.
Okay, so you see the structure of the chapters now.
Right. And if they want the complete unfiltered output, the whole fire hose, they type -VVV,
Level 3.
which prints metadata, headers, and every single parsed paragraph.
Wait, okay, I have to play the skeptic here for a second.
Go for it.
Counting V's feels a bit, archaic. Like, why go through the trouble of counting letters? Why not just program an explicit command string?
Like what?
Like -- level equals 3 or -- show headers. Something that avoids any ambiguity completely.
That exact question brings us into the cognitive psychology of the command line interface.
Oh, I like the sound of that.
It's super interesting. For a developer, iterating quickly in a terminal, right? They're compiling, testing, failing, testing again.
Rapid fire.
Yeah, typing out an explicit multi-character flag, requires higher cognitive load and more deliberate keystrokes.
Oh, I see.
It forces you to pause and think about the exact syntax of the logging command, rather than the logic of the code you're trying to debug.
What's fascinating here is the physical mapping of the keystrokes to the data volume. That's the key.
Exactly. Hitting the VO key 1, 2, or 3 times is a physical escalating action.
It perfectly mirrors the escalating amount of data you're asking for.
Yes. It creates an immediate kinetic relationship with the system. 1 tap yields a little data. 3 taps yield a mountain of data.
It totally bypasses the language centers of the brain and just becomes pure muscle memory.
Right. It's a design pattern that has survived in UNIX-like environments for decades for this exact reason.
It prioritizes the developer's momentum over strict, verbose semantic naming.
Okay, so the user experiences this fast, tactile dial on the outside. But functionally, how does the program catch those physical keystrokes and translate them into a logical filter on the inside?
Right, how's it wired?
Exactly. This moves us from the user experience into the actual Haskell architecture.
And Aang shares the code diffs for this implementation in the post.
Yeah, and the restructuring starts directly at the program's core data structure for user input. It's called args.
The args structure. Okay, so this serves as the single source of truth for the program's execution state.
Right. And before Aang introduces the verbosity logic, this structure is already managing several crucial parameters.
What else is in there?
Well, it contains the input path, directing the program to the specific file to be parsed.
Makes sense.
It holds a debug mode Boolean field to toggle standard debugging. And it contains that output format field we mentioned earlier.
Right, the export format thing, type, EPUB, all that.
Exactly. All of these parameters are populated by parsing the command line arguments, the user types.
And to handle that parsing, the source notes that Aang utilizes a Haskell library called Options.Applicative.
Yes, Options.Applicative.
This library captures the raw text entered in the terminal and maps it to the strictly typed fields within the args structure.
And here's where it gets really interesting. Aang modifies this structure by adding a new field, verbosity.
Okay.
And they assign it the type of int, an integer.
Oh, wait, so the physical off characters entered by the user
Are scooped up by options, applicative, and magically translated into a single integer.
Wow. -v becomes a 1, -vv becomes a 2.
Exactly. Deep in the code is just a simple number.
Capturing that input as an integer, rather than, say, a list of characters or some complex custom type, that is what makes the subsequent filtering so performant.
Right, because numbers are easy to check.
Exactly. But once that integer is locked into the args structure, it has to cascade down through the application's architecture to the specific functions that actually execute the printing.
Which is tricky in Haskell.
Very. In a functional language like Haskell, this state management is handled very differently than in an object-oriented environment.
Yeah, because in an object-oriented language like Python or Java, a developer might just initialize a global logging object.
Right, or use a singleton pattern. They would set the verbosity level once globally, and any function anywhere in the program could just check that global state before deciding to print.
Just look up at the sky and ask, what's the verbosity?
Exactly. But Haskell forces a much more explicit approach. You cannot rely on hidden global state.
No secrets in Haskell.
None. If a function deep in the call stack needs to know the verbosity level, you must explicitly pass that integer down to it through the function arguments.
Hand to hand.
Hand to hand. You see this clearly in Aang's code diffs. The primary parse function originally took 3 arguments.
Right. It took the raw text as a byte string, the file path, and the debug mode Boolean.
So Aang has to modify that function signature. Now parse takes 4 arguments, inserting the verbosity integer.
So now the parse function is aware of the volume level.
And the cascading continues. The parse function eventually calls a downstream function named print content.
The endpoint.
Exactly. This is the endpoint. This is the function holding the megaphone.
Right.
And previously, print content took a single argument, the token it was instructed to print.
It had no awareness of user intent at all.
0. It simply printed whatever it received.
But after the architectural change, print content requires 2 arguments. It needs the int representing the verbosity and the token.
So the state of the volume dial is being deliberately handed down the chain of command.
From the user's physical keyboard.
Captured by options. Applicative into the args structure.
Passed through the parse function.
And finally handed to print content.
It's really beautiful when you trace it like that. Okay, so now that print content possesses both the token and the verbosity integer, we arrive at the actual core logic. the filtering mechanism.
All right, how does it actually silence the noise?
How does the code evaluate that integer to determine if a token should be printed or suppressed?
Well, Ang utilizes Haskell's pattern matching to evaluate the tokens, which honestly provides a far more elegant solution than standard conditional logic.
Yeah, because if a developer were using a massive if-else block,
Oh, it would be a mess.
they'd have to write logic that says, if the token is metadata, check the verbosity. Else if the token's a header, check the verbosity and also check the header level. Else if the token is a paragraph,
It becomes this deeply nested, highly brittle block of code.
super hard to read.
But pattern matching allows the print content function to destructure the token and apply specific rules concurrently, just based on the token's type.
It just looks at the shape of the data.
Exactly. The function essentially says, oh, I see you are a tmeta token. I will route you immediately to the metadata rules.
So let's look at how Ang configured those specific routing rules, starting with that metadata.
Right.
The tmeta token contains the title, author, and index of the document. For this specific token, Ang implements a rule that completely bypasses the verbosity integer.
Oh, really? It ignores the dial.
Completely. In the code diff, Ang uses a wildcard character, an underscore, in the position where the verbosity integer would normally be evaluated.
I see. And in Haskell, that underscore explicitly tells the compiler to ignore that variable for this specific pattern.
Right. The logic dictates that metadata is simply too critical to ever suppress.
Which makes sense. If a developer is running a parsing tool on a file, they fundamentally need to verify they are operating on the correct file.
Yeah. Suppressing the title and author would render the debug log useless, even at the lowest verbosity.
So the system guarantees the baseline context is always preserved. Metadata always prints.
Always. But the truly brilliant implementation of pattern matching happens when the function routes a header token.
Yes, the headers. The notes detail how headers inherently possess a structural hierarchy within a text.
Right, like a volume represents a massive division, so it is designated as a level 1 header.
And a chapter is a subdivision of a volume, making it a level 2 header.
Exactly. The token itself carries this integer-based hierarchy.
Okay.
So Ang writes a single line of logic for the header pattern. It just says, when verbosity is greater than or equal to level.
Oh, wow.
Yeah. The code aligns the structural hierarchy of the text directly with the verbosity integer defined by the user.
If we connect this to the bigger picture, this demonstrates the power of clean logical programming. The integer of the user's intent perfectly maps to the integer of the data's structure.
So what does this all mean? It means the program is essentially self-aware of its own architectural constraints.
It doesn't need to consult some massive external matrix of logging rules.
Right. The token arrives at the function and presents its level. I am a chapter, which makes me a level 2.
And the function checks the user's dial.
The user set the dial to 1, you are a 2, you do not meet the threshold, so you are suppressed.
That is fantastic.
It operates exactly like a bouncer at a club checking IDs against a tiered VIP list.
A bouncer, I love that.
Yeah. Are you VIP level 1? Proceed. Are you level 3? Sorry, tonight is a level 2, and above night only, you have to wait outside.
That alignment is what separates just functional working code from elegantly designed code.
Totally.
By matching the integer of the verbosity flag directly to the integer of the book's structural hierarchy, Ang resolves an overwhelming noise problem with absolute minimal logical overhead.
Just a few incredibly elegant lines of logic.
There are no convoluted overrides or edge case handlers. The data dictates its own visibility based on a single comparative operator.
Which brings us to the final routing rule, handling the paragraphs.
The bulk of the text.
Right. The p-paragraph tokens make up the vast majority of the document. Now, Ang notes that these paragraph tokens are actually passed through a summarize function before they're even sent to print content.
Oh, okay. So attempting to condense the output by truncating the strings first.
Yeah, exactly. But even in a summarized state, outputting every paragraph destroys the readability of the terminal.
Well, sure, because the sheer frequency of paragraph tokens overwhelms the structural tokens.
Right.
Even if a paragraph is shortened to, say, 50 characters, printing 1,000 of them completely buries the 3 or 4 header tokens. The developer actually needs to verify the parsing structure.
It brings the megaphone right back. So for the t-paragraph pattern, Ang establishes a hard-coded threshold when verbosity is greater than or equal to 3.
Level 3.
The paragraphs are completely locked behind the highest possible interaction level.
A developer has to explicitly type -VVV to release them.
Exactly. The default state of the system is absolute silence regarding the bulk data.
If we step back and review the entire implementation, we are really looking at a masterclass in information architecture here.
We really are. Let's recap this journey for you, listening. We began with a developer totally paralyzed by the output of their own tool. The debug log was just an undifferentiated wall of text.
Right, drowning in logs.
But by leveraging past experience from the TXT2book project, Aang implemented a multi-tiered volume dial using the -v flag convention.
They captured those physical keystrokes into an integer within the arg structure using options.
Applicative. Pass that state deliberately down the functional chain to the print content function.
And utilize Haskell's pattern matching to evaluate that integer against the inherent hierarchy of the data itself.
It's so clean. And while the Haskell syntax and the functional paradigms are fascinating on a technical level, the core takeaway from Aang's post applies far beyond software engineering.
Oh, absolutely. Even if you never write a single line of Haskell, this entire exercise is fundamentally about intentional design.
Yes. And the aggressive protection of human attention.
Aang built a system that refuses to offer the highest resolution of data until it is explicitly, intentionally demanded by the user.
The tool assumes that, by default, the user only requires the metadata to orient themselves.
It respects the developer's cognitive limits by forcing the noise into the background.
And we rarely apply that level of strict architectural filtering to the systems we interact with every day.
That's so true. The default state of modern digital environments is maximum verbosity.
Yeah. And that is the exact thought I want to leave you with today as we wrap up this deep dive.
That's a good one to ponder.
Think about the platforms you engage with every day. You're constantly refreshing news feeds, the algorithmic timelines, the email inbox is overflowing with newsletters.
The push notifications constantly vibrating in your pocket?
Exactly. Those systems are designed to operate at level 3 verbosity by default. The megaphone is hardwired to the on position, constantly shouting the paragraphs at you whether you explicitly asked for them or not.
It's exhausting.
It is. So what would your digital life look like if you architected a strict -v counting flag for your own daily information consumption?
Wow.
What if you forced the world to only provide you with the metadata, just the titles and the authors, until you explicitly decided you had the focus to process the rest?
That would change everything.
Something to think about. Thanks for joining us on this deep dive. We'll catch you next time.